Okay, so good morning, everybody. Just two classes, I think, is decent enough to give us a perspective on what happens if we try to introduce jumps into financial modeling, right? And the first thing that I need to do is to demonstrate to you the inefficiency of the present Brownian machinery. Because when we think about Brownian motion and Ito rule and everything that we've learned so far, we like to believe that what we've learned is a complete system in some sense, that it can help us model everything that is presently there in finance. But that isn't true, right? And to give you an example of the most stark situation where the black scoles or the typical continuous model was shown up as inadequate, I would like to demonstrate to you one particular event, which is the Black Monday market crash of October 19th, 1987, right? So this particular crash, as you can see, look at the Dow Jones. The Dow Jones has appeared to follow a Brownian motion up till a certain point, which is roughly the 18th of October. And then on the 19th of October, you can see this crazy jump. And the probability of a Brownian motion making that kind of a jump, or any functional of a Brownian motion making that kind of a jump, is ridiculously low, right? This particular jump. This thing, it's crazy. Everything else up till here, you could say it's Brownian. You could say that this is reasonably Brownian. But what has happened here is something that certainly you cannot describe as being Brownian, right? And Dow Jones actually lost 22% of its market share this day. So it's a rare event, no doubt about it. Having said that, it is still an event which, if we can predict it, and we should be able to hopefully, then we should be incorporating it into our model to improve accuracy, right? And as you can see, mostly jumps tend to, at least in the financial situation, describe roughly extreme events. But in more recent modeling, it's been found that jumps can be made more common. So for instance, if you want to do extreme fine analysis of certain situations, it's okay to have jumps which not just encompass rare events like this Dow Jones crash, but even more common events. So this is just one motivation. There are multiple such motivations. There is a motivation that comes from the 2008 crash, for instance, right? The first model, which incorporated jumps, was actually introduced by Merton in 1976. So black scoles were the ones who came up with the typical continuous model as we know it. And Merton's model, which included jumps, ensured that that model, which was relatively complete, won them the Nobel Prize in Economics in 1996. I think it was posthumous. One of them was probably expired by then, but nevertheless, the other two were certainly around to collect, right? Now, there are two problems. If I say that you should let a process jump, the first two natural questions that should come to your mind is, when should it jump and how should it jump, right? So for example, if I say that the process should jump often, that still doesn't mean that I should make it jump every 1 second or every 2 seconds, right? I want to make it somehow random. How random should I make it? What is the correct notion of randomness? And how much should it jump, right? Should it jump by a small amount, by a large amount, by a random amount potentially, right? For the first one, what we do is we take an example of what is called the Poisson process. And the Poisson process is the most fundamental jump process. Now, the thing is that you have all seen jump processes before, right? For example, you've seen something called a simple symmetric random walk, which is just you start from zero and every second you jump 1 second to the left or 1 second to the right, right? Now that's also a jump process. It just sits at one place and then jumps, sits at that place, jumps, sits at that place, jumps, right? But the point is that the Poisson process is actually a version of that same process, which is much more regular in some sense. And what regularity exactly means is what I will come to. It turns out that the answer to the first question is inspired from the Poisson process. When should the process jump? And how much should it jump? The interesting fact is that it can be almost chosen freely. You can decide pretty much your jump distribution in any nice manner. And we'll come to that also later, right? Yeah, you can say that. So by a Poisson process can be obtained as a scaled version of a binomial process. Sure. And how much should the magnitude of the jump? Yeah. So for example, in this diagram, the jump was by this much, right? You can imagine that on another day, there might have been a jump, but it might have only been by, let's say, half the amount or something. something like this. It would have jumped only half this amount, and then it would have continued this. This might have been another different sample path on another day. Right? Or on another day, it would have basically not even jumped. It would have just continued. So the question is, when does it jump? And if it jumps, how much does it jump? Right? You have too many options over here. And the answer to all these questions is given by, as I said, the Poisson process. Now, how does the Poisson process jump? The Poisson process has exponential inter jump times, right? So recall what the exponential random variable is. It's basically a random variable which for a parameter lambda has the jump distribution lambda e to the power lambda x as its density, right? And this is probably the easiest way to understand it. The probability that the random variable doesn't jump until x seconds is given by e to the power minus lambda x, lambda being a fixed parameter, right? Now, what beyond this? Beyond this, you take a look at the a process which is basically accumulating exponential times, right? So for example, maybe from 0, I start, and then I wait until maybe x1 is equal to 1.5. So I wait until time 1.5. Then I jump, I go up by 1, and then I start again. And then maybe this time x2 is 3.5. So I keep going until time 5. Then I jump. Then I go. Maybe x3 is a much shorter time. Maybe it's just 0.25 or something like that. So then at 5.25, I jump again. So you can see that you just get a sample process which is jumping at certain times. And these times are random exponential lambda random variables, right? And that is what you can see the definition of NT over here is. So you have SN, which is basically talking about how often these events are occurring. So they're occurring at times Sn. At each time Sn, the random variable NT will jump up by 1 to reflect which small n is going on. So how many of those jumps have occurred? And you can see that each jump is of size 1 because what is happening over here is that NT, so each time one of the Sn occurs, like let's say you go from S9 to S10, at S10, NT becomes 10 from 9, right? So from 9, it has become 10. So the jump at each stage is by 1, by plus 1 all the time, right? And this process is called a Poisson process. Now, in case this still wasn't clear, think of the NT as an arrival process, which is exactly what, for instance, somebody in a first course in calculus would tell you, right? The exponential random variable is very good at modeling arrivals of people, customers into stores, arrivals of stock into warehouses and things like that, right? Suppose people walk into a store with roughly lambda people walking in every hour. So lambda indicates a rate at which things are happening. So the way to think of it is, if lambda is 1, one person walks into the store every hour. If lambda is 10, the store is crowded, right? Yeah. In a limiting sense. In a limiting sense. Yeah, correct. Yeah, as in, like, yeah, of course. Somewhat. Right? So the number of people who have walked in before T hours is then NT. Basically, how many arrivals? So if you think of each person as an event, how many events have arrived before time T? That is NT. Right? Now, of course, if you just replace people with stocks, so NT updates when a stock jumps, then all you need to do is you just need to start using it in models. So you just need to say, okay, well, if I say that a stock jumps whenever a Poisson process jumps, then all I need to do is I just need to make sure that this Poisson process is amenable to mathematics. I should not end up creating a model that's so complicated that I can't do any math with it, right? Which has 77 different parameters that I need to sit and learn on paper. No way, right? Instead, I should be able to demonstrate to you that the Poisson process has some amenability, that you can play around with it, that it's not a relatively difficult object. Any questions so far? The number of, so if I that there'll be one crash every. So you expect N9 to be close to 9, but it may be 8, 7, 10, something like that. That's the rough idea. Of course, in real finance, things will be very different. So there, what exactly a stock jump means might be pretty different. I mean, it depends on what you call as a market crash or what you call as an adverse event, right? Anyway, this is the nice fact about the Poisson process. Now, if we call it a Poisson process, there has to be a reason we use the word Poisson. And the answer to the question that why do we use Poisson is the fact that the number of arrivals up till time t is basically Poisson times lambda t. So just try putting t equal to 1. It's basically saying that within 1 unit, lambda people would have come on average, right? That's what it's basically saying. Because if you remember, the expectation of a Poisson random variable is just a parameter, right? So roughly speaking, you're saying that one person comes in, lambda people come in every 1 second or whatever, 1 unit. So roughly every t units, lambda t people come in. Around lambda t, what is the fluctuation? The answer is it's a Poisson fluctuation. Now, in order to answer that question, I need you guys to recall what do we need to do to prove this? So in order to prove this, what we need is we basically need machinery that allows us to get a hang of these quantities. See, because NT depends on Sn. So if we don't have a hang over what Sn is, we do not have a hang over what Nt is. So this is the guy we need to study first. Yeah. Independent. Oh, I didn't write it, is it? Sorry. That's independent. So, thanks. That's a very important point. If you don't assume independence, the process might become very stupid, right? For example, if all the xi end up becoming the same, then you're basically saying whatever the first time for the market crashes, the second market crash will happen exactly after that much time. The third one will happen exactly after that much time. That's too much predictability. So any such model will be rejected on day one. Right. So to prove this result, I need you to recall the following result, right? This result tells you that if you have two random variables which are independent and with densities f comma g, then their sum has this density, right? And you can understand why this is kind of true. So f of y is roughly the probability that x is equal to y. And this is roughly the probability that y is equal to small x minus small y, right? So of course, all this is very, very rough. These densities don't represent actual probabilities, right? They represent sort of the density of the probability, cumulative density function at that point. So what you're doing is you're saying that the probability that, okay, what just happened? Sorry. Roughly, you're saying that the probability that x plus y is equal to x, small x, is you're integrating over all possible y's that small x can be. And then you know that if capital X plus capital Y is small x, then one of them will decide the other, right? So if capital X is small y, then capital Y must be small x minus small y. So then you just integrate over this. Instead of summing, which is what you would do if they were discrete random variables, you just integrate over. Right? So this formula is not too suspicious in any manner. Now, let's do this with x of lambda. If you do this with x of lambda, then what do you get? The sum of two exponential random variables is, as you can see, f of y is lambda e to the power minus lambda y. G of x minus y is lambda e to the power minus lambda times x minus y. And this integral goes from 0 to x because, as you can see, both f and g, they only take values if the parameters are positive, right? So y needs to be positive and x minus y needs to be positive, which means that y needs to start from 0, but it can only go up till x because otherwise x minus y would become negative. So once you take this integral is pretty simple. The lambdas just come out. You just get e to the power minus lambda into x. In fact, you just combine these two and you just get e to the minus lambda x. And then you just get an integral from 0 to x of 1. So you just get lambda square e to the minus lambda x. And then this is just integral 0 to 1 dx, which is just x, right? So this is your density. And by the way, on a different note, this thing is called a gamma random variable, right? So the sum of two independent exponentials is called a gamma random variable. So this one is gamma of 2 comma 1, right? Sorry, 2 comma lambda. Okay. Now, in more generality, this is what S2 is. Sn you can calculate by induction. So this is the density of S2, sorry. The density of Sn can be found out using induction. No, density. This is the thing that you integrate to get the CDF, the PDF. That's what you call it, right? Probability density. So in more generality, this is the Sn that you can expect. And how do you prove this? As I said, induction, right? Because if you take x1 plus x2 all the way up till xn, then that's just nothing but x1 plus x2 all the way up till xn minus 1 plus xn. So this guy and this guy are two independent guys. So let's say I call this guy as z and this guy as y. Then I just apply this formula with y plus z. Right? So I know the density of y, I know the density of z. I just need to perform the integration. The support is 0 to x ojas because if you look at this formula, the formula on top, which talks about the general density of x plus y, there the integral goes from minus infinity to infinity, right? But small f and small g for an exponential random variable, they're only supported on 0 infinity. So that means that small f of y is positive only if small y is greater than 0, and small g of x minus y is positive only if y is less than x. Right? So now you just need to show this thing by induction. And this is precisely what we will proceed to do. And as you can see, it's not a very difficult calculation, right? Because it turns out that exactly the same thing that we saw in the one-dimensional situation, sorry, in just x1 plus x2, the same thing happens. There's lambdas that combine. Then maybe let me indicate it in red. These two guys combine and they again give you just e to the minus lambda x. And whatever is left is just y to the power n minus 1 by n minus 1 factorial. And the integral of that, thankfully, just by the way it's built up, is just y to the power n by n factorial, which when integrated from 0 to x gives you x to the power n by n factorial. Right? So this is not so difficult to prove. Right? And once this is true, we've discovered the distribution of the Sns. And once we've discovered the distribution of the Sns, we then need to just connect the Sns to the NTs. That's all we need to do. And how do we do that? The point is the NT is the arrival process of the Sns, right? So basically, NT tells you how many S's have crossed up till time t. So NT is greater than equal to K if and only if the number of arrivals so far is at least K, right? So if Sk, which is the time of the kth arrival, is less than equal to T. So does anybody need an explanation of this? Please let me know. I can explain it again. Huh? SKs are increasing, right? So what am I trying to say? I'm trying to say that, see, remember, if you think of NT as an arrival process and SK as the time of the kth arrival, then there have been at least K arrivals if and only if the kth arrival came before this time. Right? This is a very logical statement to make. So that tells you that the probability that NT is greater than equal to K is this guy on the right, which is the density of, which is basically nothing but the probability that Sk is greater than equal to T. Sk is less than equal to T. And this guy is nothing but the probability that Sk minus 1 is less than equal to T. Right? Now I just need to subtract them because I need the probability that Nt is equal to K. Remember, I'm trying to prove that Nt is a Poisson random variable. So for that, I need to get the probability that is equal to a particular number. I just need to subtract these two guys. And once you see these two integrals and you think, how the heck am I going to get the Poisson thing out of this? The first thing you must be thinking of is you have something like an integral. You're going to get a number minus something that's an integral. What kind of technique do you expect will lead to a result like this? What kind of equality of expressions have you seen? Integral of something is a number minus integral of something else. Very, very close. Something like that. Integration by parts. So fundamental theorem of calculus also works, you're right. But integration by parts is what will be used here. And as you can see, this is precisely what works. So if you look at the red parts and you look at the blue parts over here, the red parts are being integrated and the blue parts are being differentiated. So the red part, lambda e to the minus lambda x, its integral is minus of e to the minus lambda x, and the derivative of x to the power k by k factorial is just x to the power k minus 1 by k minus 1 factor. So you just get probability of nt is greater than equal to k. Just following the chain, you get e to the minus lambda k, lambda t to the power k by k factorial, plus integral 0 to t of this guy. And that's just thankfully equal to the probability that nt is greater than equal to k minus 1. So we are lucky. We have gotten this quantity, right? And this quantity, by definition, is equal to the probability that nt is equal to k. And this is, in fact, what happens. Yeah, exactly. So now we have shown that NT is the Poisson distribution. By the way, this is only true for K equal to 1, 2, 3, and so on. Because you see, you can't obviously use this for K equal to 0. What does this mean? But then if I have done it for K equal to 1, 2, 3, and so on, obviously for K equal to 0, like if a Poisson random variable isn't 1, 2, 3, it's obviously 0, right? So just by complementarity, you'll get the same answer for 0. Right?
NT is just like supremum of those.
No, it's the number of arrivals up till that point. Yeah, like what's the last SK which has happened in some sense. So NT is what is the last SK that came before T. The K such that the SK came before T. What's the largest? Right? So think of it this way. Like, okay, fine. Let me go back and clarify this yet again. Right? Just go back to the arrival idea. So look, think about it this way. X is the inter-arrival time. So people are walking into a store. Each person is walking in an exponential time after the previous guy. So Sn is the time when the nth guy walks in. Nt is the arrival process associated to Sn. So Nt is saying up till time t, how many people have come? How many people have come? The answer is that the time for the kth person to have come should have come before t. So the kth person should have come before t. If that's true, then you look at the largest k. And the largest k will tell you what is the last guy that came before t, right? And that is basically nt. So this is telling you that if people are arriving exponential, exponential of lambda with an exponential of lambda of each other, then the number of arrivals within time t is Poisson with parameter lambda t. For Sn, lambda still means rate. So it still means lambda people are walking in every hour, right? Or something like that. Now, what is true about the Poisson process? Apart from the fact that, we know what the marginals of the Poisson process are, is something pretty interesting. It turns out that a Poisson process is a Levy process. In other words, it starts at 0. I think that is pretty obvious because nobody has arrived by time 0. At any two times, whatever two times which are completely distinct from each other, if I look at the number of arrivals here, and if I look at the number of arrivals in this time interval, then they are independent. So basically, between time 0 and time 1, and between time 4 and time 5, and between time 8 and time 13, the number of arrivals are completely independent, have nothing to do with each other. And the last one is the fact that there is stationarity. So in other words, if I'm looking at how many arrivals are there between 0 and 2, and between 8 and 10, these have the same distribution because both of them are time intervals of 2 minutes or 2 hours or whatever unit you're considering. So in other words, the number of arrivals, the distribution of that quantity, how random it is, it only depends upon the time interval within which I'm doing my tracking of how many people are coming, right? And these three traits are the traits of what is called as a Levy process. So a Levy process is basically any process which starts at 0, has independent increments, and has stationary increments. There is one more condition called stochastic continuity. We will not go into. right? Hmm. Right? Then it's a Brownian motion, right? But this doesn't have continuous paths. That's the point. NT, so what I'll show you is, wait, or maybe I'll go there now. Uh, these are the sample paths of the Poisson. So they're clearly not continuous. You can see, for example, take a look at any one path of the Poisson process. Take a look at this blue guy. It's going up. It's like, it basically looks like a process that's just going up by one at different points, right? So it's not a continuous process. It's jumping. It's jumping here, it's jumping here, it's jumping here. So even though it might appear like the quadratic variation has some pattern, and we will find out what that pattern is later, that has thankfully nothing to do with that particular theorem of Lev. Right? No, it won't be zero. It won't turn out to be zero. I'll tell you what it is later. Right? Now, what does this proof rely upon? This proof relies upon the fact that the exponential random variable is actually something called memoryless. Now, what does this mean? This basically means the following. So there are two random variables that fall under the that fall under this memoryless category. One of them is the exponential, and one of them is the geometric random variable. Right? Now, this loosely means that suppose that I have waited for the next market crash for T years, and I'm asking, okay, what is the probability that it's going to happen within the next S years? The answer is, you should imagine as if these T years haven't passed at all, as if nothing has even happened, and you're just restarting your same question. So probability that X is greater than T plus S. So if you have already weighted T, the probability that you will weight S more is the probability that at that time at which you're even asking the question, which is time T, the probability that you will wait S. So basically your waiting time is memoryless. It doesn't matter how long you've waited for in order to find out how long you're going to wait beyond this point. Right? And that's pretty amazing. This, by the way, is the only random variable. So x of lambda is the only continuous random variable which is memoryless. And similarly, geometric random variable is the only discrete random variable which is memoryless. So memoryless is based on the conditional idea, right? So for example, if I know that the Bernoulli random variable is greater than 0.5, I know with certainty it's 1. So it's certainly not memoryless. It's certainly not memoryless. Right? This is saying that I don't know what my random variable is going to be if I know it's beyond a certain. So I don't know anything about it. Its distribution is completely independent. Right? So let's see how this particular property is used. And as I said, what we need to do is when we talk about independence, we need to do conditioning. So we need to look at conditioned on the past, how is the Poisson process behaving in the future, which is our focus on the next slide. So to do this, for any t greater than 0, you consider how long you're going to wait from this point until the first arrival after this. So for example, I'm right now at time 100 and I'm asking myself, how much longer do I have to wait until the next person comes into my store, right? Now what I'll do is I'll also condition on how many people have come so far and what was the time when the last guy came. So nt is equal to n means n people have come so far, and Sn is equal to tau means the last person came at time tau. So for example, let's say small t is equal to 100. Let's say small n is equal to 7. And let's say small tau is 97. That basically means that at time 100, I am asking, when is the next person going to come? Knowing that 7 people have come so far and the last person who came 90, at the time 97. Right? Now let's just analyze everything that's happening over here. And what I want you guys to tell me is to understand very carefully. So see, the first statement is pretty obvious because if zt is greater than z, that means that the exponential waiting time, yeah, yes. Zt is still the measure. Yeah, yeah. So if zt is greater than z, then what does that mean? That means that in addition to how much I have already waited, which is time t minus tau. So in this context, that's 3, right? So I've already waited 3 minutes or whatever. What is the probability that I have to wait z minutes? It's the probability that the time from the previous arrival is going to be at least z plus 3, right? That's exactly what it is. So this line to this line is not too difficult. What I want you guys to tell me is how I go from this line to the next line. Just think for a minute. Obviously, I have the answer on the next slide, but just think for a minute. A second to third, yeah. Just think. X is the inter-arrival times. They are the exponential inter-arrival times. So xn plus 1 is the time between Sn and Sn plus 1. I have not assumed anything, Rushil. No stationarity assumed. No, nothing is assumed in this. Everything that the only things that we know is xn plus 1 is the inter-arrival time. Nt is n, Sn is tau. That's it. Yeah. Okay, so the memorylessness doesn't get used. In this jump, nothing gets used apart from these three statements. Absolutely nothing gets used apart from these three statements. That also I can promise you. Just focus on these three statements. Focus on the nature of the process and tell. Arrival time, right? Exactly.
So far, I haven't witnessed any person coming in. So it by common sense.
Exactly. That's right. That's roughly the idea, right? Wait, I'll just explain that thing again. So what's happening, boss? What's happening is that, see, let me use my example, okay? So at time 100, I have 7 arrivals so far. The last person came in at time 97, right? So this is 97, this is 7, and let's say small z is 3. Okay? So now this is my question is that how, so at time 100, what is the conditional probability I have to wait for 3 more minutes? At least 3 more minutes, right? 3 more minutes. Now, what is this statement telling you? This is telling you that if you focus on what this quantity is, just calculate what is z plus t minus tau, and that's just 6, right? So this is telling you that this is the same as the probability that starting from 97, I have to wait for more than 6 minutes. Exactly, right? So is that step clear? Yeah, I mean, not independence. The point is that if I know when my last guy came, then starting from now, the amount of time I have to wait is the same as starting from then, like just the sum. Right? So I waited 3, I have to wait 3 more. Something like that. Right? So no. This is a probability. Probability means by definition, we're not looking into the future. We're predicting the future. We're not looking. Right? No, not the same. Nothing to do with that, right? So all the statements, all these jumps in each of these statements, huh? Yeah, exactly. Yeah. Exactly. Exactly. So given nt is equal to n and xn plus 1 is greater than z plus t minus tau, we must have this guy n. So if xn plus 1 is greater than z plus t minus tau, we must have xn plus 1 is greater than t minus tau itself, right? So basically, you're saying that if nt is equal to n, then that means that, sorry, this is small n. You're saying that between the last arrival and now, there was no arrivals. So that means that the inter-arrival time between this time, 100 and 97, is at least 3. That's all it's saying, right? So this statement is tantamount to saying that the last arrival was whatever. The last arrival was small n, so that the inter-arrival time n plus 1 is at least 3. So this one to this one is okay. The next statement follows because xn plus 1 is independent of Sn. Right? All these guys are independent, one behind the other. So we know that Sn, once the nth person has arrived, it doesn't matter. Everything that's happening afterwards is independent. Yeah. And then we're done. Now this last one follows because of the memoryless problem. So xn plus 1 is greater than z plus t minus tau. Given xn plus 1 is greater than t minus tau, is just the probability that xn plus 1 is greater than z, which is e to the minus lambda z. So just very quickly, second equality is if you're given that Sn is tau, you know that the event nt is equal to n is the same that the last waiting time, the n plus 1th waiting time is greater than t minus tau. So those two events are basically the same. And the third equality comes from the independence and the last comes from the memoryless nature. But what is the most amazing part of this? The most amazing part is that this guy, e to the minus lambda z, it doesn't depend on n. There is no n and there is no tau. No n, no tau. So you've completely forgotten how many arrivals there were before. You've completely forgotten how many people came before and when was the time that the last person came. Completely forgotten, right? And that is the basic reason why both stationarity as well as independence fall. Now, yeah. This one, huh? So Aman, okay, let me take the same example. So let's say n equal to 7. Let's say small t is equal to 100. And okay, let's take small z is equal to 5. Okay. So 105. So what is this? What is the first guy? The first guy is the probability that if 7 people came before 100 and last person came at 97, what is the probability next person comes after 105, right? Now I want you to focus on the English interpretation of the second event. The second event is the probability that if 7 people came before 100, so 7 people before 100, and last person came at 97, what is the probability that starting from the last person, look at what is t minus tau. T minus tau is 100 minus 97. Yeah, exactly, right? So 3. So see, if I'm at 97, then from 97 to 100, I've already waited 3 seconds. And then from 100 to 105, another 5 seconds. So what's the probability that from last person, I have to wait at least 8? Yeah. Yeah, you had a question? The quadratic variation thing I'll come to later. Okay. That's something that requires its own interpretation. I'll come to that. Yeah, you're right. It's on 12%. Yeah. What do? We move this back, is it? We do that? Okay. Sure. That would be helpful. Is there like a... Do one of you guys have like a, this one, what is it called? The adapter, right? Something that you can plug into this so that it can go into a socket.
No, but what do you want to charge?
This iPad.
Charge.
Lightning only, I think so, yeah. Whatever this type C, right? Just checking. Yeah, whatever. Either one is helpful. Yeah. Yeah. No, just give me this part.
But then if you see it like this, just use the cable. Just use the
Oh,
cable.
just use the cable. Yeah.
And if it's short, then I can give you this long thing as
No,
well.
but wait. How do I now attach this to? I need to attach this there.
Yeah, okay. So then I'll just give you the longer.
Just give me the long.
You have to put this down, but you have to use this cable because it's
Okay. Thanks.
No.
Okay, so I'll put this.
Yeah.
Here.
Just be careful. गिरना जाएगा.
Yeah.
नीचे
Sorry,
रख दे, नीचे
where
रख
did
दे.
I even go? Done, it's charging. Thanks, man. Thanks. Yeah, thanks. That's okay. That
वो गिरना जाएगा because no, the
No,
thing
no.
is it falls. that's
दिक्कत
why.
नहीं होगा, दिक्कत.
Charging?
Yeah, it's charging. Okay, guys. Sorry for that interruption. Very quickly, now let's go back to the same argument. And let's remember that just by independence, not only is ZT independent of the previous guy and when he came, but it's actually independent of all the previous guys. Why? Because if you just go back to this argument, in this argument, what we have done is we just had Sn is equal to tau. Now over here, if you have Sn minus 1 is tau n minus 1, Sn minus 2 is tau n minus 2, all these guys will go from this step to this step because of independence. Because xn plus 1 is not just independent of Sn, right? It's independent of Sn minus 1, Sn minus 2, all those guys. So each one of them will go. In other words, if I think about what is happening to this process, what is happening is that once the nth person is arriving, I don't care about how many people have come. I don't care about when those people have come. But the probability that the next person is going to come is e to the minus lambda z within z time, right? And furthermore, not only that, you can take a look at further inter-arrival times after z1. So if n people have come, what is the probability that the next person is going to come within time z? What's the probability that after that person comes, the next person is going to come within probability z? What's the probability that after that person comes, the third person is going to come before probability z? Each of these guys, using a very similar argument, which I'll skip, is going to be exponential, and these are all going to be IID exponential random variables, which basically means that once a person has arrived, the process just renews itself at time t. It is nothing but a new Poisson process with the same intensity starting after any arrival, right? And that automatically implies both stationary and independence, because if you are renewing yourself, that means that you're renewing yourself by forgetting the past. So automatically independence follows. And when you're renewing yourself, you're basically following the same distribution as the original process. So if originally I had to wait Z for a new arrival, even now after renewal, it's not like the process's law has changed, right? Probabilities haven't been changed. Poisson process. No. I mean NT, right? Because what is ZT? The ZT is together build up the NT, right? Right? Yeah. This argument is rough. I'm not saying it's fully rigorous. It just means to give you an idea of how the exponential random variable plays a role in this. Because if I replace exponential with uniform, all this will fall apart. It will all fall apart. But still, if you do that, there is still a theory for that, and that is the theory of renewal processes. So the theory of renewal processes comes in, and by the way, this also gets used in finance. It's not like it doesn't. It gets used a lot in insurance, particularly. This is where the inter-arrival times are IID, but not exponential. So they could be IID U01, or they could be IID Poisson, or they could be IID gamma, right? Something like that. Something else, basically, right? Stationarity basically means that the number of people that arrive in any time interval, any fixed time interval. Let's say any 2 minutes, if I take any 2 minutes and I ask how many people will come in that 2 minute interval, that's independent of where that 2 minute interval is on the real line. So whether that 2 minute interval is now from now to 2 minutes from now or tomorrow, let's say 12:02 p.m. to 12:04 p.m., it doesn't make a difference where I take that 2 minute interval, where I start it. That's what's stationary. Still Poisson of 2 lambda. You get it? So Poisson of 2 lambda, which means it's independent of where that interval is located. Only the interval's length matters. The same thing is true for the Brownian motion, right? Bt minus Bs is normal with 0, t minus s, right? The same thing is true there also. N tau plus t is still a Poisson process. Yeah, correct. Exactly. But this won't be true for a renewal process. For a renewal process, you will have a set of renewal times at which that thing will happen. But otherwise, it won't happen for all stopping times. So for example, you can see how this Poisson process looks. And what you can see here is that there is this general trend, right? Most Poisson processes tend to be in and around a line which kind of looks something like this. They mostly go in and around that. And you can see this is a straight line. And the slope of this line is precisely lambda. Because, not lambda, sorry, 1 by lambda. Because you expect lambda arrivals every hour, which means that every 1 second you expect 1 by lambda, right? Is it lambda or 1 by lambda? Let me just. Lambda. Sorry. Yeah, my fault. Yeah. No. Right. You slope should increase. Exactly. You're right. Yeah, it's lambda. Here the expectation is different. What is the expectation? NT is, yeah, exactly. So NT is Poisson of lambda. T, right? So expectation of NT is lambda. Now, what is a martingale here? Over there, the Brownian motion itself was a martingale. Over here, the process is increasing. So obviously the process, if it's increasing, it can't be a martingale because a martingale needs to be fair. Whereas if a process is going up, it's obviously unfair in one direction. So you need to subtract something to make it unfair. And what do? Typical thing, you just subtract its mean because you know that a martingale has to have the same mean. So in order to make sure this process has the same mean, you just subtract the mean at each point, which is just NT minus lambda. Independence then just follows, right? And this guy is a martingale because you can just see how it looks, right? Just the typical thing that we do. So when we have a random variable, with respect to a filtration, we break it into 2 parts. Part 1, which is independent of that filtration. Part 2, which is in that filtration, literally like measurable with respect to it. Now, NS is a guy which is measurable with respect to Fs. So expectation of NS given Fs is just NS, whereas expectation of xt minus NS given Fs is just expectation of xt minus NS because that's just independent, right? So if you're conditioning on something that's completely independent of the underlying filtration, the best guess that you have is just the expectation of that random variable. And now this quantity is just minus lambda s because xt is chosen to have 0 mean. Right? So expectation of xt minus ns is just minus lambda s. So you just get ns and minus lambda s. So ns minus. So this is a martingale. Now, what about NT itself? Thankfully, NT is a strong Markov process. So not only is it a, process which has independent increments, stationary increments, all that stuff, it's also a strong Markov process, which, like Ojas said, basically means that if I take any stopping time with respect to that Poisson process will restart from the stopping. So after that point, you'll basically forget what happened before tau. After tau, it'll basically happen like things are starting fresh. Yeah. Yeah. For this, because NS is super nicely behaved, you will have a much richer bunch of stopping times. For the Brownian motion, it's much more restricted. right? NT shows many nice kinds of self-similarity. So for example, just think about it logically. Okay, what is N of CT? The number of arrivals up till time, say 2 times T. So take, say TC is equal to 2, N2T. Now that means you're asking how many people have come up till time 2T. Now that's just going to be twice the number of people that have come till time T, right? Because by stationarity, 0 to T and T to 2T are going to have the exact same distribution. So that's basically what's going to happen over here. And then this is something that's very common. So for example, suppose I am running a store and you are running a store. I have my own Poisson process. People come to my store at that rate. You have your store. People come to store at your rate. Combine our stores one random day and we get a Poisson process with the rate of arrival lambda plus lambda prime, because suddenly the people who are flowing into your store and my store are now combined. Right? This logically makes sense, and it is in fact. And these things are not very difficult to prove, by the way. The last one is very interesting, and this is called a marked Poisson process. So for example, suppose that many people come into my store. Okay, some people misbehave and some people are very nice customers. I want to give them stickers, right? And some people are very bad. I want to chuck them out of the store. The thing is that I can basically create separate Poisson processes if I have a probability with which bad people enter my store and a probability with which good people enter my store. Or if you think about it from a stock market point of view, imagine that every time your stock jumps, you call a stock jump as bad if it's bad for you, and you call it good if it's good for you. Maybe somehow you ended up earning money from it. Oh, wow, wonderful. If you ended up losing money from it, oh, heck, I hate it. So suppose that somehow everything that jumps, it jumps with independently having a probability P of being good for you and a probability 1 minus P of being bad for you. Then guess what? The good events themselves and the bad events themselves, the good jumps and bad jumps, separately form Poisson processes with the appropriate intensity. So you know that out of lambda guys who come, P are going to be good, which means every unit of time, lambda P good guys are going to come. If bad guys are going to be 1 minus P, then out of every lambda guys, lambda into 1 minus P guys are going to be bad. So this is logical. And this can be generalized. So for example, suppose you don't want good and bad, but suppose you want to have good, bad, and medium. You can do that also, right? That is more complicated. That will come when you look at compound Poisson. There you can perform like changes of measure. You do a Girsanov theorem and you can tilt towards your favored outcome. You can do it. I'll come to that at the end. Either this lecture or if maybe we are a bit delayed. So next lecture. Okay. Yeah, you can always do it for any Poisson process and you can do it in any manner that you wish. No, you need to assume that. You need to assume that every jump will be independent, good or bad. You need to assume that. If you have correlation between jump amounts, then you're in trouble. So for example, if you say something like, if the first guy is good, the rest are going to be good, then you won't get a pass. Yeah. That will come in the compound Poisson. Don't worry, I'm coming to that. Okay. But first, what I'll do is I'll talk about stochastic integration with respect to a Poisson process, because this is so simple that you'll probably feel like, what the heck, right? Now imagine a process that whose sample path looks like this. Exactly. You just do piecewise integration. See, the Brownian motion has a problem that if you try and do piecewise integration, you'll run into trouble because its pieces look crazy. Right? But this guy, you just need to look at where it jumps. Because where it jumps is where there are differences, right? And where there are differences is where you need to integrate. So the answer is surprisingly simple. Almost surely, if I fix omega, this process nt of omega, t going to nt of omega. Now, this is a question that I need to ask you guys. It's piecewise constant. That is pretty obvious because it sits between non-arrivals. Why does it jump only at finitely many points between 0 and t? Why finitely? Why can it not jump infinitely many times? Yeah, basically, the number of jumps is exactly nt, and nt is Poisson of lambda t, and Poisson of lambda t cannot be infinite, right? So basically, nt of omega is finite almost surely because it's a Poisson random variable. Right? Correct. So basically, you're right. Right? Now, it's of finite variation. Now, once the minute something is of finite variation, you have something called the Riemann-Stieltjes integral specifically for that, which is nothing but the Riemann integral, except that when you are taking the weight of an interval, instead of taking xt plus 1 minus xt, you take g of xt plus 1 minus g of xt, where you're doing dg. So if you're having integral f dg, you'll just have f of xi, g of xi plus 1 minus g of xi. So each integrals, each length intervals weight will be changed. And it turns out this can be simplified much more. So don't worry about that. I'll do that also on the next slide, right? Very quickly, what's the definition of Riemann-Stieltjes integrability? If you have two functions, let's say the second guy is monotone. This guy doesn't need to be monotone. It can be of something called bounded variation. Let's ignore that. Define the upper and lower Riemann-Stieltjes integrals, which, as I mentioned, is nothing but you just weight the intervals by g of ti plus 1 minus g of ti instead of going ti plus 1 minus ti, right? So instead of integral f of x dx, what you're doing is integral f of x dg of x. And see, if you think about what x is, this is a g. So if g of x is equal to x, this is nothing but the typical Riemann integral. Ti plus 1 minus ti plus 1 minus t, right? So what do you get? You call an function as Riemann-Stieltjes integrable if, basically speaking, the partitions can be made thin enough to make the upper and lower Riemann sums converge. And when they converge to a quantity which you call the Riemann-Stieltjes integral f dg. The magical thing is that this process, if you think about it, it's only jumping by one. It's only jumping by one. So if I take a partition, like let's try and take a partition, maybe I'll indicate this partition in blue. The only things in this partition, so if you think about like what is g of xt plus 1 minus g of xt, here it's 0, here it's 0, here it's 0, here it's 1, here it's 0, here it's 1, here it's 0, here it's 1, here it's 0. In other words, remember what is g over here? G is nothing but nt, right? Because we're doing dnt of omega. So because of that, the nt function, the only things in the partition which end up mattering are the jumps, right? So suddenly, you should not be so surprised when I tell you that this formula for the Riemann-Stieltjes integral is really simple. Each jump is of size 1. To add to the comedy, each jump is of size 1. So furthermore, this formula is true in generality. If you have a piecewise constant function, and at each point, you call its jump as the difference of the left limit and the right limit, then for any continuous function on 0 comma t, you just have the integral of 0 to t of f dg is just nothing but at the discontinuity points, you take the jumps and then you multiply the jumps with f at those jumps. Because you're counting how much it jumps on, right? So for example, suppose that you're doing, yeah, exactly. So here the jump is of size 1, right? Whereas if I jump of size 2, then my integral should end up getting multiplied by 2. So that means that the jump value matters in the ratio. So fx times delta g of x. And of course, taking this to the Poisson process, where we know that the Poisson process only has jumps of size 1, we get this form. So the stochastic integral is nothing but you just find out where the particular sample path jumps and just take the sum of x's at each point. So it's really, really simple, right? Really, really, really simple. And furthermore, You can even do something like this. This I'll come to, of course. But just take a look at what's going on over here. Integral 0 to t xt. Now I'm not integrating with respect to nt, but I'm integrating with respect to nt minus lambda t. But guess what? That's not a problem. I just split this into dnt minus d lambda dt of omega, right? And so I just get a dnt term and I get a lambda dt term, right? So this kind of thing we will also see later. Yeah, this thing is called the compensated Poisson process, but we'll not talk about that. So before moving to the general situation, how do things look generally? Let's talk about compound Poisson process. Yeah. Oh, no. There's no logic. Like I'm just making the, so for example, both these terms are individually easier to understand, right? Whereas the term on the left is harder to understand. That's all I'm saying. Which is the first term? I'm confused. xt. Oh, you're saying why not just focus on d and t omega? Oh, no. I'm just saying this as a general formula. I'm asking you to specifically focus on the left-hand side. And I'm saying that if you have something complicated like the left-hand side, you can just break up the process, the integrated process into two parts. One part which only has jumps and one part which doesn't have jumps. You get it? That's all I'm saying. So now we'll define compound Poisson processes. So like Aman was saying, what if you want the process to jump up and down? As I mentioned earlier, you can make the process jump how much ever you want. So if you jump by 1 all the time, you get the Poisson process, jump up by 1, because you're counting arrivals, right? That comes from the idea that one person comes, so you add 1 to your number. But if I decide that I want to not add 1, but I want to add an IID amount by a distribution J. So I have IID random variables, J1, J2, etc. And I let the underlying Poisson process run. But instead of jumping by 1, I jump by Ji at the ith. So suppose, for example, that I don't just look at a customer coming, but I'm like, yeah, if this customer is coming, he's probably going to spend this much amount of money in the store. So maybe this guy is going to spend 10, that lady is going to spend 30. Oh, she looks rich, she's probably going to spend 1,000. I don't know, right? So you keep these IID random variables in your hatch and you add that IID random variable at that point of time. That is a compound Poisson process. And you can see this is how it looks. Xt is at every point where it jumps or there is an arrival, you associate a weight to that arrival. And obviously, these random variables need not be positive. They could very well be negative. Right? So what's an example of a nice Poisson process? Well, okay, before that, this is also a Levy process. Turns out that this process also has independent stationary increments, and it's also a Markov process. This is slightly harder to prove. I will ignore it. And more generally, Poisson processes, compound Poisson processes, they all come under the umbrella of what are called as pure jump processes, which I'll come to define later. Now, what's an example? Let's take this example. J is Bernoulli plus minus 1 with probability half. So basically, it's nothing but plus 1 with probability half and minus 1 with probability half. So that's nothing but a simple symmetric random walk. So you're just at a point 0. You wait for an exponential amount of time, exp1, let's say. Then you jump either left or right with probability half. So you jump here, let's say left. So you're now at minus 1. Now you wait here for a new exponential of 1 amount of time. You either jump right or left. So maybe you jump right. Now you wait here for exponential 1 and so on. No. It's a random variable. Exponential waiting time, right? Exp of 1 is a random variable. So I'll choose to wait at each point for a random amount of time. So at 0, I will sit for some time, which is random. Then I'll jump either left or right. Wherever I jump, I'll sit there for some time, which is random. Then I'll shift left. You get it? Okay. Now, expectation of xt, if it's a compound Poisson process, is expectation of J times lambda. So for example, if you have j is just equal to 1, which is the Poisson process situation, where it always jumps up by 1, then expectation of xt would just be lambda t, right? Which we saw. Now, why is this true? This is just true because of conditioning, right? If I think about expectation of xt, the problem with xt, the problem with the formula for xt is that it's got this weird random object on the bottom, right? We don't know. This is random. So therefore, you can't just apply linearity of expectation and be done with it. You have to condition on that object. So why don't we just condition on it? Conditioning on it. So if I condition on nt, remember what is xt? Xt is summation over all s such that nt jumps at s of js, right? And of course, s less than equal to, right? Now, if I'm conditioning on nt, I'm basically conditioning on how many jumps there have been, right? So if there have been, so if let's say nt is equal to n, then xt is equal to summation I equal to 1 to n ji, where these ji's are iid, right? Because there have been exactly n jumps. And now what is xt? What is expectation of xt? Just linearity of expectation. It's just n expectation of j, because you have n different guys who are happening. So n expectation of j times what is the probability that there were n arrivals. And if I just take expectation of j out, I just get expectation of j summation n equal to 0 to infinity, n times the probability that nt is equal to n. And this quantity is nothing but the expectation of nt, right? Just by the definition of what expectation means, this quantity is nothing but the expectation of nt. And the expectation of nt is lambda t. Right? Now, the best part of all this is that one can prove that xt minus expectation j lambda t is a martingale. This one, here to here. So, Ojas, imagine fixing nt equal to n. Okay. If you fix nt equal to n, you're fixing the number of times the process jumps before time t, correct? Each time the process jumps, an increment of size j is added. So xt, conditioned on there being n jumps, is just a sum of n iidj's. Is that clear? So the expectation of n is just n times expectation of j. So xt minus expectation of j lambda t is a martingale. Right? And in particular, what happens if expectation of j is 0, like with this case, where it's -1 with probability half and +1 with probability half? Well, the process itself is a martingale, right? Because then expectation of j is just 0. So then xt itself will be a martingale. And in particular, this exponential waiting time, simple symmetric random walk, is both a martingale and a compound process. So it's a wonderful process in that way, right? Now, what is a pure jump process? It's, yeah. No, j just needs to be something that has mean 0. If j has mean 0, then the appropriate compound Poisson process will automatically be a martingale. Yeah. That's the key idea. That's the key idea. Yeah. Expectation of j into lambda. Correct. Yeah. Now, what is a pure jump process? It's just any process whose paths are piecewise constant, right? But what do we do when the process jumps? Like when a process jumps, there's always the question of what is the value at the jump point, right? So what we do is, by convention, we say that the process should be right continuous, but have left limits. So basically, for example, you take a function like this, f of x is equal to 0 if x is less than 0 and 1 if x greater than equal to 0. This function, its graph looks like this, right? It's basically 1 at x equal to 0. So it's right continuous, but it's not left continuous. because from approaching from the left, the limit at this point would have been 0, but it's actually 1, right? So we assume that pure jump processes have right continuous paths. So that's just a convention. It just ensures that the points are being weighted correctly, right? We also assume that xt only jumps finitely many times between any two time points. Hmm. Exactly. We'll come to that also later. We'll come to that also. Now, you can actually relax this assumption. It turns out you can actually relax the assumption that it jumps only finitely many times, but this is very difficult. You can make it jump infinitely many times, but let's not even talk about that. That is pretty difficult, right? So what are examples of that? Xt can be Poisson, compound Poisson, but it can also jump at other times. And it can also have dependent jump sizes, right? So for example, suppose Jt is t times Bernoulli of half, then my jump time at time t depends upon the value of that jump, right? What time is that jump happening? So then obviously it's not going to be, it's going to be pure jump, but it's not going to be a compound Poisson or a Poisson process, right? So of course, it's not going to be Markov, not going to be a martingale, not going to be a Levy process, but we can still define stochastic integrals because all we need is this formula. This one. If you just have a piecewise constant guy, all you know is the Riemann-Stieltjes integral is just the product at the discontinuities of the value of the jump times the function value at that point. So fx delta g of x. So just think of it this way, right? Integral f dg is summation f delta g. That's the best way to think of it at the discontinuities. Of course, if it's not a discontinuity, delta g will just be 0. So that makes no sense. But this is the best and nicest way to remember that form. Okay. Now, what happens if you are doing integration in more generality? Integration in more generality should look something like this. You should have the ability to have a Brownian component, to have a non-Brownian, non-random, I mean a random component, but with finite variation in some sense, and a jump component. So this is your Brownian component. This is your jump component. And this is just some drift component, random drift. Here you do not have an Ito's correction, right? Yeah. With the jump process added on. You will have Ito's correction in the Ito lemma, in the appropriate Ito lemma you'll have. Exactly. That's it. But with jumps. Okay. Right. So this is a jump process. This process is what in every book will be called as a jump process. So it's basically a process that has continuous parts. It has a Brownian part, but it also has a jump part. Hmm. Hmm. Hmm.
What you look at XT is X0 plus some Ito's lemma random. But then integrating not with respect to X, you're integrating with respect to DBS and all of that.
DBS and all, correct.
So why integrating requires that requires integrating?
Oh, is this a mistake? Wait.
No.
No, I don't see a mistake. Something off? Yeah. Oh, there's no motivation behind integrating with respect to dx's other than the fact that it's just mathematically easy at times. I mean, see, at the end of the day, if you have an Ito process, like if you have a stock which is moving like excess, it's just easier to say that the, like if I'm trading with respect to this stock, should I convert the stock into the Brownian motion formulation and then state the price process in terms of that Brownian motion formulation? Or should I just state it as integral phi x phi s dxs? It's just much easier to say phi s dxs, right? Because you're just saying that this is my stock, this is the amount that I am betting, this is my portfolio or whatever, this is my gain, which is integral phi s dxs. So it's just much notationally easier. Yeah. Exact. Hmm. Hmm.
Is a meme which is kind of
Yeah. Yeah.
here the jump path is kind of,
Hmm.
my question is the meme itself.
I think there are things called jump processes with elasticity. I think that's what you should look up. Okay. There's something called the elasticity of a jump process. You should look that up. But you can see now it's super easy to integrate with respect to any jump process. Because as you can see, just take any adapted process phi s and just integrate phi s with respect to dxs. And now all you're doing is you're just integrating phi s into gamma s d. Oh, this is b, sorry. And then integral phi s theta s ds, and then integral phi s js, which is just, as we know, summation over phi s delta js, right? Where over all the jumps. So stochastic integration is really nothing new per se, right? This is the nice and easy way of understanding it. If for a jump process, I write xt in this manner, dxt is gamma t dbt plus theta t dt plus djt, where I now have a jump process which is also in place, then just multiply both sides with phi t and you know exactly what is the process, which is the stochastic integral of phi t with respect to xt. That's just integral phi t dt, phi t gamma t dbt plus integral phi t theta t dt plus integral phi t djt, which by definition is equal to this particular thing. Right? So stochastic integration is something that is very normal per se. But the minute I have the process taking infinitely many jumps, it goes haywire. I'll just explain. Yeah. So I think it's worth maybe either ending or trying to work out this example. Suppose xt is nt minus lambda t. If dxt is given by this breakup, then what are gamma, theta, and j? Yeah. Gamma should be 0, right? This thing has no Brownian part in it. Theta should be negative lambda, right? Because negative lambda. And what is j? J is just nt. J is just nt, right? It's just nt. Okay, so gamma is 0, theta is minus lambda, and j is nt. Right? So now what you do is, I will try and integrate a particular process using stochastic integral ideas. So let phi s be equal to this guy. It's equal to 1 if nt jumps as s, and it's equal to 0 otherwise. Now let's calculate integral phi t dxt, where xt is this guy. Let's calculate it. It is nothing but minus phi t lambda dt plus phi t dnt, right? Because the gamma part is not there, as a 0, right? Now, what is the best part about all this? This number phi s, when we are integrating with respect to dt, integral phi t lambda dt, this number, this function phi is equal to 0 almost surely, right? Because it's basically 0 jumping, 0 jumping, 0 jumping, right? If you're doing a Riemann integral of a process like this, it's 0, right? So this guy is just going to be 0. Hmm.
In one case, you were just counting.
Yeah. Yeah.
Now
It's just 0 because this is the traditional integral, right? This is the traditional integral. So the traditional Riemann integral of this guy is just 0 because it's a process that's 0 almost everywhere, right? Almost, not almost surely, almost everywhere. So therefore, only this guy remains, only phi t d and t remains. I didn't even need the final. Countably many jumps, which automatically. Yeah, correct. Here you would not even need that. Right. And now what do you see? Phi t dxt is summation of phi s d delta ns, because that's literally the definition of the integration with respect to that kind of phi t d and t basically. And then what is phi t? Phi t is just delta nt. So delta ns into delta ns is just delta ns whole square. And then delta ns is just 1 if it jumps and 0 if it doesn't, right? Exactly. So delta ns square is also 1 if it jumps at s and 0 if it doesn't. So what is this guy? This is nothing but the number of jumps that have occurred up till time t. And by definition, that's the Poisson. Where? Sorry, sir. Right, very. Right. Yeah, that's right. Yeah, it would be equal to, sorry. Lad, yeah, you'd have the opposite. You'd have the opposite, right? Yeah. So phi t dxt is actually dnt. This guy, the integral of phi t with respect to xt is actually just a Poisson process. Quite surprising to think about it, but that's how it is, right? So very quickly, what have we seen so far? We've seen jump processes and integration with respect to them. But what have we seen? We've also seen that the stochastic integral. So you see, what is the stochastic integral over here? It's nt. Nt is not a martingale. So if you know that, if I take an integral with respect to a Brownian motion, I got a martingale. Over here, I lost that martingale property while doing a stochastic integration. So what do I do in order to retain it? What do I do in order to retain martingales? And what about the Ito rule? What about the Girsanov theorem, right? Yeah, exactly. We could integrate. Xt is a martingale. Phi s is adapted, but integral phi s dxs is not a martingale. What is going on, right? And the answer is, what is going on is the following. Adapted is not enough for jump process. And why? Because as we saw, the example that we just saw is that this guy is a martingale. This guy is adapted, but this is not a martingale. So why? Why is it that a stochastic integral is not a martingale? Yeah, basically continuity issues. Let's take a finance perspective on this before we end. If you imagine that a stock value is performing like a martingale, a person who is able to do this, who is able to basically run this portfolio, what is this person doing? So imagine that someone tells me beforehand when the market is going to crash. What I'll do is, just before the market crashes, I'll sell all my stuff. And then the market will crash, it will jump, because I knew it's going to jump just before that. Just after it jumps, I'll buy everything. And then I'll keep going. Next market crash, I know exactly when it's going to come. Imagine that. I'll sell just before the crash comes. When it crashes, immediately I'll buy after it comes. So you can imagine that I'm creating arbitrage by knowing jumps. But fundamentally, jumps are unpredictable, right? The basic thing about a point is that jumps cannot be predicted from the left, because the jump processes are not left continuous. And lacking left continuity is kind of natural, right? Because like Rushil said, if I am going ahead in time, I don't know when the market crash is going to come. Whereas if my process was left continuous, remember what left continuity means. It means that as I get closer and closer to that time, my value gets closer and closer to that value. So in other words, as I get closer and closer to a market crash, I should start feeling more and more like there is going to be a market crash. But a jump process is not left continuous. So I have zero clue about it. Whereas Here, if I did have a clue about it, I would not get a martingale. I would be able to get arbitrage. I'll be able to win the market, right? So this means that if I need a martingale and if I need fairness, I need my portfolio to be unable to predict jumps. Ergo, I need my portfolio to be left continuous. And the statement is that if I have a jump process, which is a martingale, and I have a left continuous adapted process, then provided some integrability condition holds, the stochastic integral is a martingale. Right? Huh. And we'll end with this. Right. Huh. Maybe, okay, let me just see one more thing. Okay, just this one example, maybe. Let's take a look at this one example. If you take a look at this function, phi s, this is a left continuous function now. Because what we've done is, we've deliberately put 1 from 0 to a random time s1, and then we've put 1 after that, right? So whatever this function is, I want you to take it home, integrate it, and check for yourself that it's actually going to be a martingale. So now, okay, now we're done. Thank you.